Now I'm going to continue to develop the probability theory we were doing last time. And the first topic I want to talk about is combining probability spaces. So we saw last time how to define a probability space. For example, if I roll a dice, then I get a number between 1 and 6. The probability of each event is 1 over 6, and that defines the probability space. But I can add these two things together. So suppose if I, instead of throwing one dice, I throw two dice. Okay? So then I've got one probability space for the first dice, one for the second, and I can combine them to make a joint probability space of the total result. Okay. So suppose we've got two sets. Suppose we've got two sets. So just to keep it simple, I'm going to suppose it's finite, but there's no reason it need to be. So suppose this is one set of events, and this is another set of events. Like M, let's say. They don't need to have the same sort of events. Then we can define the set of total possible events by taking what's called the Cartesian product. So we define a new set which is called X cross Y. And this is the set of all possible combinations of events. So, as I said, for example, X can be a dice, in which case this is 1, 2, 3, 4, 5, 6. And then the combination would be the probability that the dice is equal to 1 and this dice is equal to 2 or whatever. So it's here x1, y1, or you can have x1 and y2, or so on. You can have x1 and ym, or you can have x2 and y1, or you see, you keep going all the way up to xn, yn. So x cross y is the set of all possible combinations of events. X can be something, y can be something. Okay. So I'm going to develop this using an example. I'm going to suppose x and y are two dice, which I'm rolling. So therefore, both x and y are equal to the sets. The dice takes values between 1 and 6. Right? Each dice takes value between 1 and 6. And therefore, when I take the cross product, the first dice can be 1 and the second dice can be 1. That's one possible outcome. Or the first dice can be 1 and the second dice can be 2. Or the first dice can be 1 and the second dice can be 6. And the first dice can be 1, the second dice can be, the first dice can be 2 and the second dice can be 1. And you all the way up to the case where both dice roll a 6. So we can combine probabilities of events like this. Now suppose that we've got a joint probability distribution. That means we've got a probability on this product. So suppose we have probability Pxy of x and y. So we have a probability on the joint space, on this one. So, for example, for dice, Pxy of x and y, well, if these are fair dice, the answer is always the same. The probability of any outcome is always 1 over 36, where x and y can take any values between 1 and 6. So if we have this joint probability, then we can define a probability on each of the individual spaces as well. So we can define probabilities Px on X, Py on Y, as follows. We define the probability on X, of some event X, as the sum over all possible events for Y of the joint probability X, Y. And similarly, we define the probability of event Y as being the sum over all possible results for X of the probability of X, Y. Okay. Now this makes sense, right? This is saying the probability that X happens is equal to the probability that X and Y happen, sum up over all of the possible things that Y can be. The probability that Y happens is equal to the probability that X and Y happens, sum up over all the possible things that X can be. So this definition makes sense, right? And again, for dice, we find that, for example, the probability of getting 1, this is equal to the probability of getting 1 and a 1, plus the probability of getting a 1 and a 2, plus the probability of getting a 1 and a 6. And all of these are equal to 1 over 36 by definition, so this is equal to 1 over 6. And so on. So for the dice, it's as you expect. The probability of getting any result on the first dice is a sixth, and the probability of getting any result on the second dice is also a sixth. Right, the reason I introduce all this talk about combining probability spaces is there's a very important concept called independence, which requires this theory. Okay. We say that the variables x and y are independent this is the technical term, independent, if the following relationship is true. The probability xy of getting x and y is equal to the probability of x of getting x times the probability in y of getting y. In other words, the joint probability is just the product of the individual probabilities, and this must be true for all possible results. So for all x in the space big X and for all y in the space big Y. So if this is true, then they are called independent. Otherwise, x and y are called dependent. So the opposite of independent is dependent. Okay, so let's just look at it for dice. So for dice, we said that the joint probability Pxy, whatever x and y are, is always equal to 1 over 36. Probability of any joint outcome is 1 over 36. And Px of x and Py of y are both equal to a sixth. So therefore, this is true in this case. These two things are the same. And therefore, x and y are independent. So I want to give a sense of what this independence means. The independence, if you say x and y are independent, that means the result of x in no way affects the result of y. And the result of y in no way affects the results of x. So when I roll the first dice and I get a 3, let's say, the result of rolling the second dice is completely independent of that fact. Rolling a 3 on the first dice does not make it more likely to get a 3 on the second dice. There's no connection between the two results. And that's what independence means. So x and y are independent means that the result of x in no way affects the result of y. So these things, in the case of dice, they are independent. The first dice does not affect the second dice. So that's the example of independent variables. I want just to make sure it's clear, to give an example of dependent variables. So the example I'm going to do is a physical one. Suppose we're measuring the weather, so we record the daily weather, and I'm going to do it by two different measurements. The first, x, is the weather can either be hot or it can be cold. Let's say compared to the average temperature for that time of year. So today, for example, today, the weather is cold relative to the average. Okay? And y is the variable of whether it's raining or not. So whether it's dry, no rain, or whether it's wet, it's raining. Okay, so I measure the weather today, and I say today it's wet and it's cold, for example. Okay? Now in this case, these two variables are dependent, because if the weather is wet, in other words it's raining, it's more likely to be cold. And if the weather is dry and sunny, it's more likely to be hot. So the value of y has an effect on the value of x. Okay? So these are dependent variables. So these are dependent. It's more likely to be cold if it's wet. And we can write this as an equation from the definition there for the probability of it being cold and wet is greater than just the probability of it being cold multiplied by the probability of it being wet. This is what it means for the two things to be dependent. It's more likely to be cold and wet than the product of probability of being cold and the probability of being wet. There's an important theorem then. Suppose I have these two variables x and y, and I have this probability. So given the joint probability Pxy on the set x plus y, I can make two statements. The first is about the mean. If I add them together and take the mean, then this is equal to the mean of the first one plus the mean of the second one. So if I have a joint probability and I take the total, then that's equal to the sum of the means. Okay? So if I do my simple dice example again, the average value when you roll a 6-sided dice is 3.5, because the answer is between 1 and 6. And both dice are the same, so the average value of the first dice and the second dice is both 3.5, and therefore the average value of the total when you roll 2 dice is equal to 3.5 plus 3.5, which is equal to 7. So all it's saying is if you roll 1 dice, the average is 3.5. If you roll 2 dice, the average is 7. If I roll 4 dice, the average is 14. So I can keep just adding them up. The second statement of this theorem is a similar statement for the variances. So variance of the joint total x plus y is equal to the variance of x plus the variance of y. But this is not always true. This is only true if the two variables are independent. This is true only if x and y are independent. Okay, so that's the theorem. I'm not going to prove it because it's not particularly difficult to prove and there are more interesting things to talk about. But if I have two random variables, x and y, then the mean of the sum is always the sum of the mean. The mean of the sum is always the sum of the mean. The variance of the sum is the sum of the variances only if they are independent. The example I want to give is what's known as the binomial distribution. Which I will give the symbol BNP. So this is, last time we talked about the distribution of a single trial where you try and do something, you succeed with the probability p, and if you succeed you count 1, and if you fail you count 0. So this binomial distribution is a sum of independent trials. So this is n independent trials with success probability equal to little p. So that defines what n and p means. For a single trial, this is one we did last time, for a single trial x, we found that the mean of x was just equal to p, and the variance of x was equal to p times 1 minus p. So therefore, by the theorem, the mean of the sum, so the total number of successes, that's x1 plus x2 plus xn, this is equal to x1 plus x2 plus xn. But these are all independent and they're all equal to p, so therefore the mean is just equal to n times p. Okay? Sorry, it doesn't matter that they're independent. The mean of each of them is p, so therefore the total is np. It does matter they're independent for the variance. The variance of the total number of successes, this is equal to the variance of the first up to the variance of the last. And therefore, this is equal to n times p. That's 1 minus p. So if I try to do something n times, and each time I do it, the probability of success is p, then the average number of times I succeed is equal to n times p. The variance in the number of successes is n times p times 1 minus p. So we've worked this out without actually having to calculate the form of the distribution exactly, just by using this theorem about adding independent events together. But just to be complete, I will specify the probability distribution completely. The probability of having k, where k is some number less than n successes, is given by the following. P of k is equal to n factorial over n minus k factorial times p to the k 1 minus p n minus k. So I'm not going to prove it now, but I can at least explain why this should be true. Let's suppose I take 5 trials, and I want to know what's the probability that I succeed twice. Okay. If I do 5 trials and I succeed twice. Well, how can I do this? I could, for example, succeed and fail and fail and succeed and fail. That's one way I could do it. Right? Now here, the probability of success is p, and then 1 minus p is the probability of failure. Okay, so I try 5 times, I succeed twice, and I fail 3 times. So if I multiply these all together, you see that I get p squared, that's p to the k, and I get 1 minus p cubed, that's 1 minus p to the n minus k. So that explains these 2 terms, right? That's just the probability, multiplying all these probabilities together. But then you see that this isn't the only way to have 2 successes. For example, I could succeed and succeed and fail and fail and fail. Or I could fail and fail and succeed and fail and succeed, and so on. Right? There are a number of different ways of getting 2 successes and 3 failures together. And the number of ways of doing this, it turns out, is given by this factor here. So this term is just the probabilities multiplied together for each event. And then this factor here is the number of different ways of arranging the successes and failures. So in the next class, we'll prove why it's equal to this.